All right, good morning and welcome to the first extremely well-attended EXAG session. My name is Matthew Gostoff, and I'm going to be presenting this work alongside an undergrad mentee of mine, Nicholas Lau, and my advisor, Mark Riddell, entitled Co-Creative Level Design via Machine Learning. So, big idea. What good is PCGML? I'm allowed to say this because I've done a lot of useless PCGML work. Useless in terms of like how is this actually helpful to people who want to make games or interested in like similar fields. And the answer is it's generally not. The general solution for how you get something out of a PCGML algorithm is you just sort of keep running, and hope you get some good stuff. Sometimes you can seed it, but even then you don't have a lot of control. So how can we use PCGML to make making levels faster, making video game levels faster in some sort of more controlled way so you have a sense of what you're getting out of the end. And our solution here is, what instead of autonomous PCGML, we had co-creative PCGML. So in other words, PCGML, or zero content generation via machine learning, I should probably say the whole thing just in case some people are confused. It's actually working with the designer in an iterative process to build the final level. So what would you need to make that happen? Well, you would need a level design editor interface, you need an AI level design agent, and you need a means of communicating with the AI. So we built those things. So we created a level editor. This is built in Unity. Some important features just to point out. We have this nice big screen right here in the middle. This is the actual level that you're building. We have a sort of palette of different options down here. There's these different tabs that you can use to choose between different kinds of sprites to place on the screen. You can sort of paint them on, sort of Mario Maker-like. There's a mini-map down here. And there's an end turn button over here. We'll get to that in just a minute. We then recreated 3 AI agents. All 3 of these were previously autonomous, so entirely by themselves, generating levels with PCGML. So this is Sam and Santi's Markov chain, the very early 2014 one, because that's the one that we happen to have Java code for. Our own BaseNet or hierarchical probabilistic graphical model, if you like that one, and the LSTM from Adam and Michael. So we built these 3 approaches and sort of retrofitted them in some fairly unintuitive ways to make them co-creative in this sort of structure. The structure in this case was a turn-based framework. So essentially, the human would start having control, and then the AI agent would then have control, get to make some additions to the level. Human has control back and forth, sort of turn-based design. I'm going to play a short video clip, and I'm just going to talk over it. Assuming, let's turn off that. Assuming we have loading, all right. So this is me. I currently have control, and the BaseNet agent is in the back end right now. So I just put 2 ground down. I hit the end turn button. There's a little pop-up to say the partner is thinking, and the BaseNet adds some bricks to the top. Notably, the BaseNet just said, oh, we're going to add all of these bricks, but we're putting it in place by place as just a fact to make it look like the agent is adding it in real time. I have control again. I put some grounds down. I put some more ground down. And I put some more ground down. Past Matthew was boring. Hit the end turn button again. And voila, the AI agent adds some more ground. So I'm going to go ahead and end it here. It's a longer video. It's all on YouTube if you're interested in checking it out later. But you know, it's okay, right? You can imagine potentially using something like this to speed up the level design process. So here's 3 examples, well, 6 examples, 2 levels created by in partnership with each of these AI agents. So the Markov chain is at the top. The BaseNet, I can just point like this. The BaseNet is in the middle, and the LSTM is here at the bottom. So some features that kind of jump out. The BaseNet is the only one of these that has like a lot of decoration in it, because it's the only one that's paying attention to decoration. The Markov chain gets some kind of really interesting features, but also sometimes some like noise. And the LSTM can go from like very sort of standard Mario to also looking kind of noisy, I mean, they all look noisy. There's some weird stuff going on here too. In general, they just do some weird stuff, basically. But you can sort of get a sense of what each one kind of gives you as an AI partner. But to give a more full sense of that, we ran a user study. What we did was we had people go through 2 level design sessions where they would design a level with one of the randomly selected AI agents in the sort of background of this tool. They were asked to either randomly make an underground or above ground level, and they were given a maximum of 15 minutes for each level they were designing, though it's worth noting that most people finished designing the levels well before that 15 minutes was up. And they took a survey where they were asked to rank the 2 agents they played with in terms of how fun they were to design with, how frustrating, how challenging, how good they were at design, how surprising and valuable their additions were, and which of the 2 they were most likely to reuse. So here's the results. We had 91 subjects that took part. We ended up using 84 of their results. This was primarily because sometimes people just have too much fun playing with the agents, and they would just completely ignore them, like the actual study. Or they just ignore the agents, like, hey, making a level is fun, it turns out. So the results here are a little bit confusing to look at, but they're the ratio of how frequently the agent was ranked first for that feature versus ranked second for that feature. So if we were just to read this out, the Markov chain was ranked most frequently, the most fun, the least frustrating, tied to the Bayes-Nut, the most creative, and the most likely to want to be reused. There we go. Language is hard when you've been up at 4 a.m. The Bayes-Nut was ranked, again, tied with least frustrating, least challenging, most aided the design, and that's pretty much it. Worth noting, though, that all of these ratios are pretty dang close. There's not one that sort of like wins out here. And so you might be thinking, just from these sort of bold numbers, like, oh, the Markov chain is the best. And while Sam, might agree with you, that generally seems to be the case. It turned out that statistically, none of these agents outperformed the others. So we couldn't actually find that one of these agents could be differentiated from the others in any meaningful way. And in fact, there were people who really loved the LSTM, like this LSTM comment. This agent seemed to build towards an idea, so to speak, by adding blocks in interesting ways. The general sort of breakdown tended to be that if you were building a level very much like the original training data, then the LSTM was great, good for you. But if you're trying to do something weird and out there, like the Markov chain, because it's very local, right, could be very good, or because it's very local and also somewhat probabilistic, somewhat random, it could do some bad stuff. So you had this issue where people just like different features of each agent based on their own design styles. That was sort of our major takeaway here. So what do we do about this? We came up with 2 hypotheses. One was we need to train on actual or simulated representations of co-creative level design. Trying to add after the fact, trying to retrofit one of these autonomous agents to be co-creative doesn't really work. And then second, we need to actively adapt to individual designers due to the variance in these designers. So that's sort of our hypotheses. Let's see how that shakes out. We decided to re-represent this problem, so we're going to represent it as a semi-Markov decision process with concurrent actions. If you're not familiar, this basically means that we have an agent which is capable of taking different actions in parallel. So state is now going to be represented as the level at the end of each human user turn. That's going to be our states. Our actions, each single action by the agent per turn then becomes a primary action, so like each addition of the block, with the total turn representing the concurrent action taken by the agent. This is like terms from semi-Markov decision process. It's not hugely important. And the reward, this is a little complicated. Basically, we're going to use the reuse ranking, so how likely were you to reuse it as like a final reward, so +1, -1. And then we're going to get a small negative reward of -0.1 if the user deletes some addition. So that's all of that. Now what we can do is we can create a new agent using this sort of representation, which is going to be a DQ level design agent. So we're going to take as input states. In this case, represented as a 40 by 15 by 34 chunk of the level. 34 is the number of different sprites, so this is a multi-hot encoding because we can have decorations. You have multiple things in the same slot. Then we just go through a simple three CNNs with 4x4 filters. The exact details are on the paper. And then we're going to output, well, we're actually outputting the Q table, but I've suggested here that we're just outputting the additions because we use the Q table to get the additions. This is not super important. Basically, this agent's going to predict what to add next to the level. So in this example, it's going to suggest adding clouds here and here. Okay, cool? All right. So let's run some experiments and actually check out these hypotheses, try to verify them to some degree. For our first one, as a reminder, hypothesis 1 was we need to train on actual or simulated co-creative data. It's not enough to just train on static Mario levels. So for setup, we're going to compare how the original agents perform to an agent, this DQ agent, trained on the interactions from the first study, except for 22 held out interactions with 11 users. We're then going to use these 11 users basically as like a simulation of interacting with them based on how they interacted with the agents to begin with. Then we're going to have a new baseline where we sort of simulate co-creation from Super Mario Brothers levels by just removing things and then adding them back in and saying, ooh, positive reward, you created a Super Mario Brothers level. And we'll just see how that works, still using the DQ architecture. So here are the results. This is a little bit complicated of a slide to look at, so let me just walk you through this real quick. So along this first column, we have all the different approaches. So the DQ trained on the human co-creative interactions from the first study. The DQ trained on the Super Mario Brothers sort of simulated co-creation. The markup chain, the Bayesian, the LSTM, those you've already seen. These columns further on now are the simulated sort of interactions with a particular user. So user 0, user 1, user 2, user 3, etc. And each of the little cell slots in here are the total reward that the agent gets over those interactions. And then over here, way at the end, you can't really see because the sun is blocking. Can I hold on, if I position myself just so, there we go, all right. So over here, we can't compare sort of across users naturally because they basically have completely different rewards. So what we did was we figured out what was the maximum possible reward we could get for each user and then average that. So a percentile do you get? So the max would be 100%. So we can pretty easily see just like immediately that the DQ train on interactions with people does a way better job at this sort of simulated interactions with people than any of the other approaches. But it's worth noting that the DQ trained on the Super Mario Brothers sort of like this fake co-creation thing we did is the only one of these agents that gets of these baseline agents that gets a positive score. So there is help here in terms of actually trying to simulate co-creation. Worth noting, I should have said this earlier, if there's a 0, that doesn't mean that like the agent just did blah, like we can't say if it's positive or negative. It means that we can't predict because we only have limited knowledge of what that person wanted versus what they didn't want. So we don't have perfect knowledge here in terms of the reward. So this is just a simulation of interaction. Obviously, it's not actual interaction with people. Okay, so takeaways from that first experiment. Our new model massively outperforms these existing approaches on this particular task for this sort of simulated interaction. So training on true co-creation data is the best, but simulated data still outperforms these existing approaches that are just trained on static Mario levels. So we've got some evidence towards hypothesis 1. All right. Hypothesis 2. So as a reminder, this one was that we need to actively adapt to individual designers due to the variance in design styles. So we ended up creating 2 variations of our approach. One, both of these are active learning, but the episodic variation is going to train only for each user, where we're going to reset the weights after each user, okay? And the continuous, where we're never going to reset the weights. The idea being that continuous would be able to generalize across multiple users. The problem being, if it's the case that users are varying hugely from one another, as it goes on, continuous will get worse while episodic will get better, or will stay constant in terms of how it's performing. Let's take a look at how that shook out. So same thing here, I've replicated the sort of static DQ where it's not doing active learning from the first experiment, and then we have episodic and continuous. So it's worth noting as we sort of go from left to right, episodic and continuous start pretty much identical, which would make sense, it's the same approach to start. And then as we can see with time, continuous is a little better right here, but then continuous is doing worse consistently compared to episodic. Let me just wipe out the slides again so you can see those last bits. There we go, all right. A very natural way to give a presentation. Can I just? Yeah. You could probably just play. I don't know if I can, how that works.
Twisty thing?
I can't see a twisty thing. It looks like it's closer to you, maybe?
Took a look at them earlier and I couldn't find any.
Oh, they just closed?
On the right side? Yeah, there we go. Thank you. All right, easy. Okay, so some takeaways from this. Active adaptation is helping overall. We did have a higher final average percent of reward that we were able to get with the episodic. So it's helping somewhat overall and has a very high ceiling given a reactive partner. So if we take a look at 9, for example, we went from 3.85 to 42.7 in terms of reward. Notably, you can't look at this sort of back and front. You can only look at it from top to bottom. The reason why these numbers are so high, by the way, even though we only have a +1 or a -1 at the end, is because of this like concurrent actions. Each one of the actions is going to equal sort of responsibility for the final value. So 9 is very, very high, and 9 is in fact the most reactive person, the most interactive with the agent. More evidence that designers vary too much to perfectly generalize over, so the continuous approach was doing worse by the end. So we have some evidence for its hypothesis too. It's pretty good. Okay. So let's take a look at how this agent actually performs. So this is, again, this agent interacting with me. Okay. So here's me. Going to start with some ground because I'm boring again. And then I'm going to hit the end turn. And the agent's going to place some bricks up in the sky. He really likes bricks. For whatever reason, bricks are a common denominator. Notice it's sparser this time. It is a deep queue network, so it's going to be a bit sparse. We keep the bricks, which is going to give the agent a small positive reward. And now what I'm doing is I'm going to set up this little pattern, which I'm going to try to see how long it takes for the agent to replicate this little island pattern. So hit that button, give it a second, and add some more bricks and a stair floating in the sky, which is not what I wanted. So let's get rid of that. It's giving it a negative reward, this like negative 0.1 for making a mistake. I'm going to give it a second example of this pattern. And for whatever reason, at this point, I decide to add piranha plants, because I guess, you got to have piranha plants. Why not? It's Mario. Hit that button again, and add a stair at the bottom of level. So that's closer to where I want it to be, but still not there. So add a little island. This is the third now example, but I don't finish it and see what it does. Okay, I'm going to pause real quick here. So if we take a look, this is the third example, right? And only a partial example. And it's getting there, right? So this is, it's got the ground incorrect, and the stairs are not quite right, and this piranha plant is off by like 2 blocks. But like it's getting there. It's getting a sense of what we're after. One more time. Get rid of that. Get rid of that. All this giving it negative reward. I gesture back and forth. That's just for me. That doesn't help anything. All right. Go ahead and finish out this third example. And then hit the send turn button again. And no. So a regression. We didn't get what we wanted. But it does seem to want ground. So I'll put 2 ground down. Let's see what it does. Okay.
So was this from random initialization, or is this the continuous where you build it on top of?
So this is episodic concept, but it's trained on interactions with people already.
Okay.
So it has sort of it's trying to hit like a generalized notion of like human designer, and then it's trying to like actively adapt to me as a designer. So let's take a look at this, right? It's not perfect, right? It doesn't get the island setup. It doesn't get that I want these gaps in between. But it has all of these local relationships. Like it got to put the piranha plant above the pipe. It got to put the stairs on either side. It got to put ground underneath all of that. So it's close enough that I end up being like, this is fine. I do 3 examples. All right, this is cool. And I just sort of continue going from there. The rest of that's on YouTube if you really want to watch it. But we're not going to do that now. Okay, so some major takeaways from this work. It seems that existing PCGML approaches, naively adapted by me at least and my small group of people, don't work well with code creative frameworks. Okay, that sort of makes sense. If it was made for autonomous generation of levels, it's not going to work well with code creative level generation. Okay. Training on real or simulated code creative data is crucial for code creative PCGML. That's sort of what we seem to be getting at with that first experiment, and the sort of distance, the difference in results does seem to indicate that pretty strongly. Designers vary hugely from one another. That, I think you could guess, just if you've ever talked to any designers, more than one. But it's still an important thing that we've sort of verified here as well. And actively adapting users have the potential to address designer style variance. So we're not doing an amazing job of adapting right now. It's not perfect, not across the board a success, but it does seem to be helping. Okay, so some brief thanks. Thanks to the NSF for funding this, and Unity for funding this as well. This is part of the Unity Graduate Fellowship that let me keep doing this work. And I'll end on this slide, but let me explain it real briefly. So Each pair here, so this pair, and this pair, is from a study we won't be talking about today, but is in a paper that's under review at Kai. Fingers crossed. Of a single designer, a single published designer interacting with this most recent agent, the one from the last YouTube video. So what's cool here is you can see sort of distinct design patterns sort of showing up, or design styles showing up across these three levels. They're like very different from one another. So the fact that this agent can support these different people doing very different sort of design is pretty cool. Okay, cool. So thank you all for listening. Happy to take questions. Yeah, go for it.
So first off, thanks for the talk. Very interesting. So when you were running the study, or I guess when you yourself were interacting with the new agent, it seemed that there was some retraining of the agent going on kind of live, right? And that's like the whole point of it, right?
Yep.
But did you get a sense for whether that retraining of the agent would be more frustrating for the user than using some baseline agent that they could kind of predict how it will react?
Yeah, so this is getting into like the second study results a little bit. I will say, so we had basically people to take the same survey in the second round of the study as well, and it was the case that while we can't make huge assumptions here, because we had 14 published designers whose results we ended up being able to use, but they found the first instance of creating the level more frustrating more frequently, right? So the first instance may be more frustrating, but that second instance less, because once you're done with that first level, it's adapted to you more, and so it's sort of more harmoniously for sort of filling the gaps of your sort of design desires there. At least that's what seems to be happening. Yeah, Adam.
So did you do, like, you had the first study with like the, say, yours, mine, like, and you had like the how the users ranked it. Did you, is that the future study that it's under submission?
No.
Like, did you do such a thing for the Q agent?
Yeah, so there was no baselines for this agent for the study number 2. I like that all the questions are about the second study. That's very good. It was just interacting with this agent twice, because instead of being about like looking at comparisons between approaches, the second study was more about like qualitatively, are we seeing it actively adapting consistently to people? Are people actually finding it helpful over the span of like the first to second interactions, these kinds of things.
Sorry, I guess second question. Not follow on. But like, so it seemed like a lot of the gains come from the like retraining. Do you have a belief that maybe just retraining, like the adapting model, like you said, you train a model and then fine-tuned it. Do you think that there's anything of just like saying like, oh well, I'm just going to start retraining my own model or Sam's model or my model, like, you know, and use that as opposed to does the Q agent, does the reinforcement learning actually get you anything, or is it just the retraining? Like, because sort of no offense, but like you trained a bad copy paste function, and if you really wanted something to copy and paste, you would just Control-C, Control-V.
So,
so
there's more going on. If you continue to watch the video, it's not just doing that. I was giving a somewhat artificial example there to show it picking up on a pattern, but that's fair. So the reason why we couched it this way is that by couching it as like the semi-Markov decision process, it gets us a very nice like state action reward setup, right? Which is not the case for any of those 3 other approaches, right? Like, it's the case that like we could keep like updating the sort of probability tables, right? We could update for like the final levels, like keep training on that for your or mine approaches, right? Like we could do that, but it doesn't give you this like negative and positive reward thing.
Sure, I mean, like for the sake of the like maximizing that reward, but in terms of like what a user is actually wanting, like I guess maybe that's just future work that needs to be done. Like
if you want to do it, if you want to do it, that'd be great. I mean, this agent, like the editor and stuff, is all on GitHub. If you want to download it and do the study, that'd be cool. Yeah.
Could you go back to the slide from the first study, where the user study, where we didn't find significant differences across the different models?
This one.
Almost there. So close.
Yeah.
Oh, good. So the columns here are the different kind of effectively dimensions that you're measuring. Those
different
mapping on
dimensions.
like individual questions. Did you find this fun? Did you find this frustrating?
Well, it's ranking, right? So it's
Okay.
which of the two, which of the two agents was most versus not
Okay.
as most,
Yeah.
or at least some might say, fun.
Right. So given that your hypotheses now kind of moving forward from this are really honing in on like designer styles, do you have thoughts about ways you might adapt or move forward with this type of assessment approach in order to be able to hone in more directly on designer style and recover designer style rather than kind of more generic, is it fun, is it frustrating? Any
That's
thoughts
the
there?
question. Honestly, no. It's a good point for sure. And it'd be a cool thing to look into. This very next talk might speak to that a little bit.
Oh, good.
So stick around for a few more minutes.
Will do.
Yeah.
When you were training the Q agent and then fine-tuning it afterwards, were there any metric that you were looking at apart from the qualitative things? I was
Things. Sorry.
like just seeing how it worked out. As in, I was trying to fine-tune some reinforcement learning agents on new data, and the metrics that were gathered throughout the training process didn't really say anything. The loss, all that kind of stuff. Did you ever look at something and say like, there's some information there in the pipeline, instead of just looking at the rewards?
So because of the setup of this being a semi-Markov decision process, right, there's not a lot to look at outside of a reward.
Yeah.
If we wanted to like include more things, more sort of features, then the way we do that is by altering the reward function in some way.
Okay.
And that's totally possible. And the one way that we're using right now is fairly naive, right? It's like keeping things good, not keeping things bad, and we could probably do better. Like, for example, in the second video, you saw like it placed the piranha plant, ooh, just so close, ooh, just a little bit off. And like being able to capture that in some way would be great. But we're not doing that right now.
Okay, thank you.
Yeah.
I have a question. I was thinking if I were to design like 3 levels in a row and there were totally different levels, say an underground level, an overworld level, then an athletic level, the last agent might even think I'm 3 different people, right? Because they would be very different levels with very different features. So I'm thinking if there's a way to, and I'm thinking whether the agent is adapting to my specific level design, given a few examples, or something intrinsic about me that would repeat over many levels of many different types. And if there's a way to capture that and to measure which, like if it's adapting to the last few designs or to the actual preferences of the user.
Yeah, that's a good point. So like if we get all the way over here, yeah, here we go. So like it is definitely the case that I think this is set up so it's first and second for all of these. I think that's right. So it is the case that like certain local features, right, are what it's like tuning into in terms of like because the user did this over here, the agent is suggesting like tall pipes over here, right? Like that sort of thing tended to happen. But you also got more generalized things than that in terms of sort of like repeated pattern things of like small little man, my brain's gone. Like small little like floating platform things set up in like these certain difficult to access ways, also showing up as well. You're definitely right that like we could be doing better than this in terms of getting a sort of more abstract understanding in some way of the designer's style. That's a very cool idea, and it'd be a cool thing to explore in future work. Yes?
Do you have any evidence that this is how designers would actually want to interact with a system like this?
Nope.
Okay, so this was just because I guess like the only like uses of like PCGML in the wild that I've seen are people like make a thing and then train a thing on that thing.
Yeah.
Do you think that this is a better way, a different way?
So I will say the second survey to bring us back to this thing that's unpublished is we did have a question about would you prefer to use this agent because the sort of structure was they start tutorial wise like just messing around with the editor, no agent, then first round, second round. So the final bit, we did ask them, like, would you prefer to use this editor with or without an agent? And the majority of people did say, like, I prefer to use this with the agent. Just because, like, it's more fun, it's inspiring, like, it's helpful in certain ways, like gap filling, basically. I don't know what goes here, so I just want something here, these kinds of things. But yeah, like, I don't know. We'd have to do future work on that.
Yeah. Also, I think I didn't actually see the talk, but like with the Candy Crush talk at FPG this year, where like they will use like PCG to like as starting points and stuff. So I think like it's be interesting to like work out different what are the better design modalities.
Yeah, and like I was cliffy because it's in this talk obviously, but in the paper we go more into this, like, you know, like Skyrim terrain generation was the first wave. They got like the Skyrim thing and they edited from there, right? But it tends to be this very like hit the button, see if it's okay, and edit from there, as opposed to this like interleaving sort of human-to-human interaction design process. So I thought was, what if we try to make it more like that? Don't know if it's right, who knows? But it seems to be some promise. About what we can say. All right, well, thank you all again. Let me just right for a second. Sure. Sure. I'm right over here. Okay, this is the mirror. If you wanted to separate. Feel free to use the little buttons. So going to the right, like forward on slides, and going to the left, go back on the slides.
Cool.
And there's also the middle button is the laser pointer.
Is the
Well, that's the mouse one. There's a different middle button.
this middle button.
Yeah, that's the middle button. One closer to the middle of the body.
It's like this is pretty middle.
It's pretty middle top.
Okay, so welcome to the second part of this project, in which I want to be very clear that Matthew still did like all the work for this, but I think it maybe is like nice to him to not have him present for a full hour. And this is also a bit of a strange talk in which I am, of the 5 co-authors on this paper, the one who knows the least about machine learning. And yeah, we will do this. So Matthew is going to pop up in the middle of the talk to explain some of the technical machine learning types of things. Let's talk about the issues with, from a designer perspective, using machine learning in a co-creative process, right? Where, from the designer's perspective, they hit the end turn button, right? Stuff shows up on the screen, and there is no explanation for why, right? What or why. And this is something that is sort of intrinsic to machine learning as a technique for PCG, right? In that we train on a bunch of data, we generate a bunch of things, but there's no ability for the system to explain out what it is it's doing, why it is it's doing it, what part of the data it learned from in a particular way. So we're looking at, oh, this button works really well. Whoa. Okay. No. I don't know what's happened.
The AI has taken over.
The AI, yes.
If you want to just unplug it from the USB, you can just use the
Yeah, it's like
regular
detecting
buttons.
button presses that are not on.
Bizarre.
Whoa. Spoilers. Okay, I guess I'll just come back and forth between the slides. I don't trust that machine. So in this co-creative process, right, humans need to have some kind of faith that the AI is understanding what it is that they're wanting to do, right? And humans need to understand why it is that the AI is giving them the response they do in order to better interact with a partner. And when humans collaborate with each other on design problems, right, humans develop their own standardized design language to be able to talk about their levels with each other over the course of design. And sometimes that's informed very, very heavily from theory, right? You know, did you read this paper about like these aspects of level model design, let's use that kind of vocabulary. But oftentimes we also know that designers will start to develop their own language around how it is that they want to be thinking about the problem that they're doing as they're talking through it, right? So informed by external design philosophies, but not purely using the language of external design philosophies. So what we're going to be talking about in this paper is how can we begin to capture some of that language that humans are using when they're talking about design and use it as a way to drive explanation of a PCGML agent in a co-creative system. So in this talk, I'm going to give a quick overview of design patterns. For those who may not be familiar with it, this is actually the background that I came into the project with. Talk about the difference between sort of the established design patterns literature and how we're thinking about design patterns in this project. Matthew will pop up briefly to talk about the machine learning part of how the AI is actually going to learn to use these design patterns. We'll talk about a little experiment that we did, and then what it is that we want to work on next. So let's talk about design patterns. How many of you are familiar with design patterns in some way? Oh yeah, cool. Okay, so I probably don't need to go into like a huge amount of depth on this. So the two canonical works that I think we typically talk about in the game AI community when we talk about design patterns, right, is this early work from Christopher Alexander in defining design patterns for architecture. This sort of launched the entire field of design patterns research, and actually Molly writes a fascinating book out just last year called Architectural Intelligence, which is actually about how this book in part informed like all of modern computer science. So I strongly recommend you go read that as well. And then within game design, we talk about design patterns as a way to sort of formalize game design knowledge and establish a standard vocabulary around it. I think it's important to note that this early, less so in the game design patterns literature, more so in Alexander's work in defining a pattern language. Developing these patterns is also about establishing like a design philosophy, right? And though I think we often read, or maybe have our students read examples of patterns from the design language, pattern language book, this is actually volume 2 of a series. The first volume being The Timeless Way of Building, which is like a hippie manifesto of architecture that establishes like a full design philosophy around what architecture should be and why design patterns are important for it, and how we can use design patterns to like establish like ourselves as better architects, right? And so these existing pattern languages serve as a formalization of design knowledge and also a formalization of a design philosophy. Design patterns can be hierarchical, they can be relational. It really kind of depends on like what your approach to thinking about design patterns is. They often tend to focus on structural elements of design. You know, like there's an enemy on a platform, there's a valley between these two hills. But they can also sometimes talk about experiential components to design, like a risk-reward ratio, right? So the design pattern that you will have higher reward on higher risk areas of a level. But I think more commonly in design patterns from PCG, we tend to focus on structural elements. And they often take the form of a sort of a generalized description of design knowledge with some kind of potentially parameterized instantiation guidelines, right? Like the valley between two hills, you know, like the width of the valley might vary. There may or may not be an enemy within that valley, things like that. So I talked about this earlier in the talk as well, right? But like the main problem that we have when we're thinking about how designers are going to be interacting with an agent, or even how designers are going to be interacting with each other, right, is that we don't want to just use a design pattern vocabulary in the way that I have previously done in my research, because it's taking that design philosophy of the person who defines the vocabulary and enforcing it on the people who are going to be using the tool that uses those design patterns, right? So we want to find some way to be able to capture the kinds of design patterns that, or the kinds of design knowledge that the user of the tool wants to be specifying, right? Not just that what some external person has come down and said, like, this is what the structure of a platform level is. This is working in Mario, by the way, like all good AI research. So there's been a bunch design patterns specifically for, oh, thank you, Jill. That's actually helping a lot. There's been some background work in defining design patterns for platformer games, right, talking about rhythmic structure. This is embarrassingly the first paper I ever wrote. Steve Dalskog and Julian Scalia especially use these design patterns to be able to develop procedural concept generators of some kind. And then this has been this sort of style of structural design pattern has continued into some of the work that Tommy Thompson has been doing more recently, and sort of trying to understand the differences between different versions of Mario based on the design patterns that they use. And I think it's important to note, right, that even within this this attempt from the design patterns community to specify like general purpose design patterns for everyone to use, we're still each taking really different approaches to defining our design patterns, and then expecting other people to use them. So let's talk about the system that we made itself. So I'm going to give a quick overview, and then Matthew's going to stand up and talk about how the machine learning part works. So the idea that we have is, what if instead of using design patterns that we've pre-specified to people, we let people specify their own. So we have a system where people can go in and tag different sections of an existing level with patterns that they want to use to describe those sections. We then take that sort of small body of design patterns the user has specified and run machine learning that Matthew will talk about that turns it into sort of a library, like auto-tagging things, so that they don't need to tag like thousands upon thousands of these examples. And then based on that sort of auto-tag set of design patterns, then use another machine learning technique to be able to generate portions of levels based on those design patterns. The pattern tagger interface itself is pretty simple, right? We literally just have people draw rectangles over rectangles of arbitrary size over an existing level. So they do have to be rectangular patterns, I guess. And then they type in whatever it is that they want to call that thing. And they're welcome to do that multiple times, right? If every time they see 3 Goombas in a row, they want to describe it as an enemy series, good for them. If every time they see like more than 1 Goomba in a row, they want to tag that as an enemy series, right? Good for them. And we're letting them tag it in natural language, right, to build up their own individualized library of design patterns. This is the part where the top notes say Matthew pinch hits for machine learning.
All right, so the first of 2 machine learning approaches that we're using here is a random forest classifier. As Julia mentioned, the idea here is we don't want to have people tag all existing Super Mario Brothers level content with the design patterns they want to use. That sounds like hell. So instead what we do is we take however many that they give us, however many tags they give us. There was very variables, we'll get to it in a minute. We train a random forest classifier. The way this generally works is we pass in a chunk of level that passes through a set of trees. The trees then vote on what of the existing design patterns they think is in that level, and we spit out the actual true, or the majority vote design pattern. So that's the way this one's working. And we use this after that initial user tagging to tag all remaining Super Mario Brothers content with the designer specified tags, which gives us a very large training set then to train an autoencoder. So autoencoders have been used in the past for PCGML by some folks out of NYU, Julie Degelius and Aaron Isaacson. And so we decided to use an autoencoder for this portion for a couple reasons. One is we wanted to run an evaluation, and so autoencoders are nice because what you put in you should get out, and so that's one way of doing the evaluation. They're also nice in terms of we can sort of squish together different kinds of information, force it to be in the same representation, and then extract it back out. So what's happening here, let me just walk through this real quick, is we have an input chunk of level with an associated tag that gets broken apart with the input chunk of level going through a couple convolutional layers, squishing down into an encoding layer along with the tag, and then squishing back out. So it's trying to recreate what was in it. If we were actually doing this like as a serious generative thing, we'd make it variational so that you can actually get more stuff than just what went in and like small variations thereof. But this is what we have for now and for the evaluation of this paper.
Thank you, Matthew.
No problem.
So let's talk about how we actually tested out this system now that we've got a thing, right? So we did a small-scale user study where we asked 5 designers who have really different backgrounds in approaching design to create labels for a level using, quote, a common language or vocabulary that you'd use if you were designing levels like this with another human. And through this process, we wanted to test how well we were actually learning learning tags from users and what kinds of tags people are giving, right, to give us a better sense of what kinds of vocabularies the system might need to support in the future, and then how the actual generation process is working based on that auto tagging system and whether it's responsive to the vocabulary. Awkwardly, like I was one of the people who did this thing, in part because like, as we all know, research is messy, right? And so this project started before we really know that we were going to be writing a paper about it. And so I did a set of tags with like a completely naive view of what it is that the system was actually going to be able to do. And then once knowing what the system was going to be able to do, I actually went back in and did another set of tags. But we then had 4 other designers from really different backgrounds who had no knowledge whatsoever about how the system actually works, create a bunch of tags for it. So Adam Dill, creator of the Bitsy game engine, a narrative tools designer, Dee Delaria, they're a community organizer, a web developer, and also a hobbyist. Me, who's a game design and AI professor, who then also didn't know how it worked. Kaiser Kinney, an indie game developer, and Kelly Snyder, who's an art producer, right? So people from really different roles in the games industry, different backgrounds in terms of how they interface with the design process, different goals in terms of are they typically working on like small scale indie projects, or are they typically working with large teams? These are like the 3 most common tags that each person used. But then we also have a count of how many tags they did that they were willing to put in total, which has clearly very high variance, with the lowest amount being 28, right, which is actually about the amount that I kind of expected people would do, and the largest being 259, which is like, I don't even know how Adam took a bunch of time sitting down and doing this thing. He felt like he found it soothing to like drag rectangles and type in words. But you can see even here, right, there's some really different ways that designers are thinking about what matters to them in a Super Mario level that they are then going on to design, right? So Adam is tagging like specific design elements in a level, right? Like this is what a platform is. This is what a jump is, right? And that jump is going to be sort of implicitly parameterized, right, across the different ways that jumps can be. This is what like a pipe flower is, right? So his most common tags are really focused on like small scale structural elements. My tags are very much informed by my prior work in defining design patterns, right, for levels, and my prior research in doing that. So I use very much the same kind of vocabulary that I've used in my papers talking about design patterns, probably unsurprisingly. Kelly Snyder, I'm like deliberately skipping over D and Karthik for a minute. Kelly is doing sort of at a similar level of abstraction to Adam, but I think tagging like sort of slightly larger sections of like this is a walking enemy who like walks back and forth over these sections. But then I think it's really interesting to look at these tags in particular, where the tags that they are giving are much more experientially oriented, right? Like they want to be able to talk about level design as a completionist reward is here, right? Or like this is the place where a concept is introduced that is then going to be reused in the level at a later time, right? This is a really different way of thinking about design than this is an enemy like walking back and forth on a platform, right? And similarly with Karthik, right? Like his patterns are sort of at this middle ground between level structure and broad experience, right? This is where a hazard is being introduced. This is a power up, but it's hidden, right? It's important to note that it's hidden and that's got some experiential implications for people. Describing things as traps, right? And using like terminology of experience. And just to give you an example of what some of these things look like, so this is what Adam would do tag as a platform. This is like an enormous pattern that D tag is like, this is the introduction of an entire concept, right? I was tagging things like empty pairs, like multi-level things where you can move down along the bottom of the level or move up to the top of the level, introduction of a hazard, and then like tiny little small like walking enemy, right? And it's important to note that the way that the system handles these like arbitrary sized rectangles is that we split it up into like component patches, right? If it's really, really big. So we're not trying to train on like these like ridiculously sized things. So I wanted to give just an example of the kind of thing that the system can actually output as a result of this tagging process. So over here on the left, the top picture is examples that were given for what a completionist reward is, and then the bottom right is a generated piece, right?
Yes.
Where the system is saying like the thing that most made me decide that this is a completionist reward is these coins in the top right corner, right? And when we went back and asked the initial person who tagged these levels what they thought about what was being generated based on those tags, they said that yes, it's believable that this is a completionist reward, right? Like I guess that's right. There's coins there. They actually didn't get to see that the most decisive patch was the coins, but like they fill in, right? That coins are what make that a completionist reward. But then they also went on to say, I think if I were to go more strict with the definition of phrase, I think of some other configuration to be generated that would make you think like, ooh, what a tricky design, right? So we're not quite capturing what completionist reward means to this designer, but what we're generating is like believably a completionist reward to this designer. So there's still a lot of work to do in terms of figuring out like what actually is or is not one of these patterns. There's a bunch of results in the paper, but for time purposes, and also me speaking and not knowing quite as much about the ML side of things, we really wanted to focus on like the interaction model and the design patterns and the idea of this in this talk. But you can find sort of more details around some of these experiment takeaways, right? That like autoencoding with the auto tags does better than the autoencoder without any tags at all, and also does better than autoencoder with just the human tags. So like actually generating a larger training set does perform better than generating only off of the human specified training set. And then Matthew, do you want to speak to?
Sure. So that first point, I'm just going to stand, and then I'm going to knock over my chair, but I'm going to catch it. So the random forest auto tagger beats out a convolutional neural net baseline. I think we're using AlexNet, but the results are in the paper in terms of correctly predicting what tags to put on pieces of level structure. But notably, it only has about a 20% test accuracy, which is very low. But even despite that, you get that this autoencoder with these auto tags beats out an autoencoder with just any old tags or just human tags. And the last thing here is that training this autoencoder from scratch for this process is really time consuming, assuming you don't have like a GPU and a lot of processing power. And we're going to assume that some people don't. I don't. So what you can do instead is you can use transfer learning to train initially just without these design patterns, just trying to replicate Super Mario Brothers content with this autoencoder, and then use transfer learning to then train on these design patterns as well. And that ends up even further improving these results and being faster.
Okay, so there's a lot of things that we want to keep working on next, right? In terms of interaction paradigm, and then also figuring out like what use does this have, and how do people actually want to be able to interact with a system like this. So there's sort of a desire that we want to be able to continually learn new tags and new design patterns over time, right? So you may initially tag sort of a training set of levels, right? With these are things that I think are important. But then while you're in the middle of the design process, you may start coming up sort of organically with new vocabulary, right? That you would want to be able to use to explain what it is that you're creating. So having some way of being able to add in new tags and sort of train actively on those new tags would be really nice. Figuring out when it is that the system should actually interrupt a user is just like an incredibly hard problem. Right now, we don't have interruption happening. We just say like hit the end turn button when you're ready to like see something from the AI, and some people will do that for like 5 seconds and then hit the end turn button, and some people will design an entire level and then hit the end turn button. So there needs to be some kind of better understanding of, for individual designers, based on the style of things that they're doing, what kind of model makes sense there. And then hopefully we find out tomorrow whether or not we have a prayer coming soon, a paper about how do designers currently engage with these kind of systems and how they want to be able to engage with exploitable AI systems. So with that, that brings us to the end of the hour-long Matthew and Julian show on co-creative PCGML. I want to thank the National Science Foundation for funding the portion of this work. Also, Dog School and the Dog School organizers for the most recent seminar on AI and games, which is where this entire collaboration started, actually where the tagging interface was written. Should tell you something about the quality of the tagging interface. And many thanks to the undergrad students at Georgia Tech who worked on this project who are not able to be here today, so Josh and Sean. And if you have any questions.
So thanks for the talk. Would you or maybe Matthew be able to speak to why you used a random forest classifier instead of something like
totally be able to speak to that.
Yeah.
clustering or something like that?
Yeah. Well, so we needed something. We need some kind of classifier, right? Because we needed some way of saying like, okay, here's this untagged comment or content. What tag, if any, goes on it, right? So we didn't want to use clustering for that reason. We want to use some kind of classifier, and then we're going to use a classifier. Then like, okay, what are your options? We can use like SVM. We could use a random forest classifier, which we did, or we could use like a deep learning approach. We ended up going with the random forest classifier because we could do like some depth limiting stuff to try to enforce generality, even though we had like so few training examples. And comparing that to like AlexNet, right, which is one of the best things out there in terms of doing classification of this scale, we slightly do better, but it's a very tough problem. So like, by no means we think this is the perfect solution.
And quick follow-up. With regards to how you were, so you have these design patterns defined by the users, right? So how do you classify the rest of the levels, I guess? Like, how do you choose like what chunks of the levels you're looking at?
Sure. So we go. So for any of the levels that the users didn't tag, they could choose which levels they wanted to tag of the above ground levels, just for scale. Sure. We break down all the rest of them into all possible, I think we use 10 by 10 chunks, right? And then for each of these 10 by 10 chunks, we then run this random forest classifier, which is then classifying into either no tag or any of the author tags.
Okay. So contains an author tag, right? Or like is part of an author tag. Josh.
Yeah, so did you have in your authoring interface a way to overlap labels? Did the rectangles overlap? And if so, did you entertain multi-label classification?
So we do have a way for labels to be able to overlap, right? Because it's literally just draw a rectangle on and tag the thing, and it's entirely plausible that you could draw another rectangle and it would overlap and it would draw that. And we do actually have, right, each chunk is tagged with each label that corresponds to that chunk is a part of, right, in the level.
So the random forest classifier can only tag each thing, each 10 by 10 with a particular tag. Wow, my brain's gone. But we have overlapping chunks, right? And if there's an overlapping chunk and it's tagged with two different things, it's both tags.
Yeah.
And people obviously could do multiple tags.
Yeah.
Could it generate like a completionist ditch?
Yeah.
Yeah.
Re-AlexNet, were you using the AlexNet architecture or like a pre-trained one that you then fine-tuned?
Architecture.
Just the architecture, okay. Is there a reason why you chose something that is so old and not a more modern one?
Yes, because it was used for smaller, back in the old days when we had smaller images instead of the big old images we got these days. That was our basic idea, and then also like we had it on hand already authored.
And since the tags were in like natural language, did you consider like not like particularly for something where like there's like 295 like a 295 way classification seems.
Well, so that's the number of total
That's the number of
tags.
total
Oh,
tags.
okay. So then, like for the 44 way,
Yes.
it was okay.
Yeah.
I just read the number. But so then, like for the 44, like, did you consider like trying to do like essentially like captioning or something of like essentially generate like natural language descriptions of the tags as opposed to like just recalling like, oh well, it's this one like 0000000.
So we mentioned in the talk that one of our notions here was we wanted the approach to be fast to train, right? When like a designer came in, right? And ran for us very, very fast to train, right? So you're totally right, like that we could do that, we would probably improve things, but our notion there was like probably a bit speedier.
Yeah, I think a lot of the philosophy and like a lot of the conversations we were having about this project were always like, what user is going to want to spend a huge amount of time tagging things? So how do we make it so that you don't need to do that like massive pre data selection thing, right? How do we make it so that you're not like waiting forever for like any kind of decision to be made or for any kind of training to run? And how do we make it so it runs on computers that are not like this year model, right? So I think a lot of decisions were based on that like ease of interface. How are we for time, Joe?
You are right on time.
Are we
Right, done.
Yeah.
Do we have a session share? Like, is there another?
I like such a check.
Oh no, but you're the next person, right?
No, he's the
Oh,
guy.
sorry.
Yeah. So I would say we're at time.
Okay, thank you.
Not super far. If you have a USB drive on that, you're welcome to use my thing. Okay. Oh wait, no, wait, hold on. We have. Hold on. Yeah, but. Yeah, it doesn't work. Let's make sure they're paired. Oh, could that have been the issue? Why they're having issues? Or is it like a garage door opener and it works for any of them? No. Hope not. Sincerely hope. Was yours?
Yeah, I can.
You have to click the button here. So click on that square, the long square rectangle, and then hit HDMI and pop. So that's a new setting. Yeah, and then hit HDMI. I think this is right. Unplug, replug maybe. We had some issues with having to like wiggle it sometimes. Or, like, yesterday. Yes.
Trying to make this one.
That's a lot smarter.
Yeah.
Yeah, should have done that.
Yeah.
I think that's like.
All right. Hi everyone. Really great to be here. Super excited to present our work that we've been doing for the past year or so around explainable AI, sort of an approach that we use to learn how to generate natural language rationales for game-playing agents. My name is Upal. I'm super excited to present the work that a lot of my wonderful collaborators did. Special shout out to Pradyumna. He was a master's student who worked with me in this project. He's currently at Baidu Research and hopefully coming to a PhD program near you. Work has been done collaborating with Georgia Tech, Cornell, Kentucky, but all of us are representing the Intelligence Lab led by Dr. Michael. With that in mind, let's get started. So, like it or not, right? AI is here to stay. And as the trajectory goes, there's this transformation that we see from the roles of tools to collaborators. And as that transformation happens, there is this intrinsic need to make sense of why they do what they do. And as we go by, it is not inconceivable to see a future where humans may need to directly interact and communicate with these AI systems to understand their motivations and intentions. But all that good stuff, obviously there's a challenge. Unlike human collaborators, it's really hard for AI systems currently to explain failures or unexpected behavior, and this is the important part, in an interpretable manner that is accessible to the non-expert. And that makes life very difficult to trust and understand these black box systems. And without trust, it's really difficult to foster any sort of collaboration, be it human to human or human to AI. Well, one possible way to look at this is, you may just open this black box, start debugging and doing all sorts of crazy stuff to get a forensic analysis of what's going on. But that requires training, time, and resources that sometimes we may not expect for our end users to have. So here's a crazy proposal, right? How can we make this process slightly human-centered? So what if our agents could communicate with us in an understandable manner, specifically around their motivations and using natural language? I will now go over a quick example, and hopefully this video works. I'm going to preamble this video in case the video doesn't work. This is a little snippet from FIFA. I play that a lot. I get always frustrated when something like this happens. You're playing with in a career mode with NPCs that are largely AI-driven, and in this case, I'm the team defending in the white, and something awful is going to happen to the team. All right, look at that. Oops, completely missed the whole thing. All right, okay. One more time. I guess not. All right. As you can see, that is frustrating. You almost wish at this point, right? If you're playing with a friend, you almost like, hey man, why did you do that, right? And you almost wish something like this being said. I rushed for the ball, the defenders are out of position, completely didn't realize I would miss it. My bad, right? That notion of justification, that notion of rationalization, can help you sort of understand where the agent was coming from. And this is where this larger goal of NPCs come from. In this case, we can't afford to, you know what, let's pause the game, let's start debugging, and like doing a forensic analysis on why it did what it did. I need something quick, dirty, something that gets me a quick understanding of why you did what you did, and we can move on. So that is where we are approaching this notion of human-centered sort of AI communication from this approach that we call rationale generation. We define a rationale as an explanation that justifies an action. And this is the important part, based on how a human would think. And I'm going to throw a little bit of philosophy mind at you, not a lot. We sort of take the inspiration from how humans communicate. So Jerry Fodor had this notion of how we almost translate a language of thought to a language of communication. And he called that mentalese. So we're roughly inspired by that process. And the design is sort of in the same way we use language, right? We're not necessarily using our current, right now, I'm not necessarily sharing how my neural firings are working, right? I'm sharing my motivation and my intentions and my communication skills in a way that is hopefully is interpretable and accessible to my audience. So again, this notion of rationale generation is not designed to reveal the inner guts of the system. So the intuition that we sort of approach this issue is on machine translation. So this is a fake state information, obviously, but imagine A is the goalkeeper, right? And sometimes, how could we get from here to there, right? So from this notion of like data structures and sort of like numbers to natural language. And we can do that if we start treating explanation generation as a translation problem. So that is where we primarily came from. But where does the natural language come from? Well, it comes from humans, and I'll share with you how we got the data. We're asking sort of humans to teach these agents by sort of labeling parts of, roughly speaking, the state while interacting. So at a high level, this is where we want, right? We want rationale generation that translates the events, which are states and actions, into natural language. That's the overall goal, right? And this is going to be the rough outline for this talk. We're going to talk about how we collected the data, how we trained the model, and how did we generate and evaluate the system. I'm going to mainly focus on the data collection and the rationale generation sections for the rest of this talk, and it will roughly serve as the outline for the rest of this talk. So let's focus on data collection. And just to give some context, right? Machine learning algorithms are what they eat. And what they eat is data. So you really got to get the data right to get the outputs. So to collect the data, we needed an environment. So the domain that we often use, we used in here was Frogger, an old arcade game. We built a modified version of it where people can play and explain their actions at the same time. I will go over each part of the interface in a bit, but this is sort of like you take an action, you explain the action. Take an action, explain the action. This turn-taking thing going on right here. So in terms of the data collection pipeline, the larger need is to link this game states and actions into their corresponding natural explanations. So that's the linking task that we're supposed to do. And we did this in this way. We first created a guided tutorial. This was an online task that interpreters sort of came in and took. So the guided tutorial familiarized them with the process, not only with the gameplay, but also how do you give your rationales, how do you edit them. Then the actual process happened where the gameplay and the rationales were collected, which we call rationale generation. And finally, we go through this review process where people can look at all of their rationales and sort of edit them, correct them, basically clean the data from the user's perspective, half selfishly to make sure that my work is lessened in terms of cleaning the data. But also the process is inspired that can we go from a human rationale to a machine rationale without touching the data in the middle? No handoff. And we actually thankfully succeeded in doing that. So I'm going to now talk about the rationale collection section. And this is largely in a think aloud protocol, right? And if anyone of you have done that, you can understand like some of the biggest challenges is to link what you're saying to a discrete state to what you're pointing to. And sometimes, the way we sort of do think aloud, sometimes we're thinking 2 steps ahead, 1 step behind. So one way we thought of, and we iterated and pre-tested a lot on this, like what's the best way to do this? And we found that if you could use a sort of turn-taking approach, so like you take an action, pause the game, give me the explanation, and I can start recording it. So this is what happens. After every action in this game, the game pauses for 10 seconds. After that, your laptop's microphone turns on, Google speech-to-text starts working, you verbalize your rationale. So you don't have to type, so burden on the participant is lower. And then it sort of transcribes it near real time. And you get a chance of editing it right after that, in case the speech-to-text system didn't work, because we know that system is not perfect. So this process really gives us an idea of how to get that single rationale per action. Now we can look at how do you do with all the actions. So this is the rationale review section. So in this one, you can actually, once you're done playing the game, you can go through every single action that you've done. And you can use the buttons on the back end to sort of step through and go back and forth however many times you want. The rationales come by. And a lot of pre-testing showed that our participants really appreciated that because sometimes some context was missing of a future action that needed to get edited on a prior action, and they were able to revise that accordingly. And the whole point of this review section is to minimize as many errors as possible. The goal is to get as clean a data as we can. Quick snapshot of what happened with the data. So there's 60 participants. The task length roughly was 45 minutes each. And we have 2,000 action explanation pairs that actually went into training the model. So I'm not going to talk a lot into the details, not a machine learning person, but the paper really goes into how we did the configurations and everything. But at a high level, we trained a sequence-to-sequence neural net to generate this natural language rationale. And it's a standard way of setting up a translation task. At a high level, the inputs are the state action, state tripled. I'll go into what this means. And then the target is the natural language rationale. With this architecture in mind, we had two configurations because we wanted to produce two different types of rationale. The first was what we call the complete view. So in this case, let me go over this a little slower. So this is the position. This is the state information. It's a symbolic representation. So we sort of like sprited it up and like put one symbol for each. And then the action and how many lives are left. So in this complete view, you get the complete view of the environment, and we injected noise randomly so that we wanted to force the network to sort of look at other places so that it starts picking out other details. And hopefully the intuition here was it would produce some detailed and holistic rationales compared to this view called the focused view. So in this case, it's a window input around progress. The rest is exactly identical. No noise was injected on this. And the intuition was, by sort of like putting blinders on it, I'm going to make it focus on just my surroundings. And we had prior work to show that that actually didn't work. So complete view of it. Okay, so now the main meat of the thing: generation and evaluation. Before we get into evaluation, I'm going to show you some samples of what the generation looked like. So again, these are rationales for the exact same action in the environment. What you can see in the complete view is compared to the focus view, where it's like I had cars to the left and in front of me, so I needed to move to the right. It's a very reactionary, like I need to do this because something else happened. This, you see this notion of like slightly being more long term. I want it to be more centered. So this way, I have more time to react if a car comes from this side. Similarly, just to give another example, it's the same thing. So it's almost like you're sort of saying the truck won't hit me so that I can move one spot. So there's this subtle notion of not just focusing on exactly what's happening in my 7x7 movement. Now, the golden question, right? Does this process work? How do we test for it? It's hard because there is no grammar. You cannot procedurally sort of like compare against a global set of things. This is where you sort of like asking, are these rationales plausible from a human perspective? So we did what most people do. We did user studies. So we have two mixed methods user studies that try to unpack these human perceptions of these rationales. The two experiments are, the two experiments are, one is with the focused view system and an identical one with the complete view system. So we wanted to compare the focused view and the complete view against some baselines. Mixed methods here sort of refer to, we did both qualitative and quantitative work. So let's look at the study design. So it's again an online study, a total of 128 participants, equally split into two groups. And each participant, the study comprised of 5 videos of Frogger taking actions and explaining itself. And each action was actually accompanied by 3 rationales for sort of comparison purposes. You have the exemplary ones, like the best one, the best human explanation for that action. You have the candidate one. So for one experiment, we have the focus view. The other one, we have the complete view. And the other baseline was a random, right? And the goal was to see, first of all, are you doing better than garbage? Which is random, right? Hopefully we do. And then how actually close are you to the exemplary one? So that's the overall goal of this, right? And but how do you rate it along, right? Like you have to evaluate it along certain dimensions or categories. So for each action, our participants rated the rationales across 4 dimensions. And they not only rated them, they also justified compulsorily why they did, why the rating was that way in a free text response. So the first dimension is confidence. This is basically, is the rationale giving you confidence in the agent's ability to do its task? Second one is human likeness. Does the rationale look like it was made by a human? Third is adequate justification, sort of looking at the justificatory qualities of this thing. And the fourth is understandability. So like, does the rationale give you why the agent behaved as it did? So with that in mind, I'm going to quickly go over some snapshot of the quant results first. So both the configurations actually outperform the lower baseline. So the baseline is right here in blue, and the candidate is in red. As you can see, it's pretty big for both configurations. It's kind of big. But also what's interesting, right? Between the green and the red, they're not that far away. So that's actually pretty neat when we looked at the data. Like, not only beat the lower baseline, but also was pretty high to the upper one. But then it's sort of like this unsatisfied position, right? Like you need to know why. Why was this the way it was? So this is where the qualitative piece comes from, right? So to understand the why behind these ratings. So we analyzed the open-ended responses, and we looked for emergent patterns of reasoning and themes that occurred. We clustered those themes, and then we iterated till consensus was reached. With that in mind, I'm going to go through quick highlights of how the 4 categories that we talked about, confidence, human likeness, adequate justification, understandability, some of the qualitative key findings from there. So recall, confidence is just the participant's faith in the agent's ability to complete the task. Some things that work really well is when the rationale was giving recognition of environmental conditions, it was showing some awareness of upcoming dangers, and it sort of exhibited some notion of long-term planning. What didn't work was perhaps redundant information, like don't tell me the obvious things, tell me something interesting. Things mischaracterizing, like calling a truck a log. So if the network sort of mischaracterized it, it was penalized. Or if the random rationale, right? If you randomly selected and the action was in the water, and the rationale was a randomly one from the cars, there's a mischaracterization. So that didn't really give confidence understanding. And again, if it's just short-sighted, like I'm just doing a reactionary move, then that could use confidence. Next is human likeness. So just recalling this is sort of like it looks like it was made by a human. And this one was kind of tricky. It was a little tricky because the perceptions of these rationales matter what the participants thought of their perception, a mental model of what humans are like. So if they thought air is human, then rationales with errors, typos, were perceived as more human-like. And if they thought that computers are stupid, then things with less errors were perceived as more human-like. So this was an interesting tension we saw, and I think the qualitative data really helped us understand, because without that, we wouldn't have the perception of like why, because it's almost like all of them are almost equally human-like. Next, we have adequate justification, and this sort of boils down to, are you aware? Like, are you aware and are you able to judge your surroundings? And are you able to justify your rationale with the end goal in mind? And if you have lower accuracy, again, like mischaracterizations in the environment, I don't really think you'll justify your action very well. Or if you're just giving me the short-term answer, like I'm going one step up, I don't know about that. Finally, with understandability, it's sort of like how well the rationale conveys the motivation behind the action. And it boils down to this relatability. And actually, this is a quote from a participant. I loved it. It's like, I did the same action. Reasons I would give for this action, right? This notion of like human-centeredness, like, would I explain this action in the same way? Answer was yes, great. Or, if you fail, again, this accuracy of description hinders understandability. And inability to sort of contextualize the situation. It creates, it sort of like, doesn't give you a notion of motivation. So this sort of ends the rational generation and evaluation piece. The key takeaway for us from the qualitative things is it helps us understand the why behind the ratings, but also contextualize user perceptions. Why are these ratings happening the way they are? And in a way, we hope others and us can reuse to improve the design of these agents, right? So I've taken you through data collection, training model, and rationale generation. Now it's time to wrap this bad boy up. Okay. We think, based on the work that we've done, rationale generation is a plausible approach to human AI communication. It's not the one-size-fits-all solution, but I think there's promise there, and our early work sort of gives us hope that this is a direction that we can take further. From an engineering perspective, I think we can really tweak around these network configurations and figure out where, because we went through like from a windowed input to like a complete view, and I feel like there are many intermediates in the middle that you can tweak around, and you can totally see like modular design where depending on where you are in an environment, you may want a long-term explanation versus a quick short-term explanation. From a design perspective, we hope that our user study provides insights for others and ourselves to inform future design of NPCs. And finally, we hope that all of this can improve our user engagement by leveraging some of the transferable insights that we can get from this body of work to others. Finally, I really want to thank a few people. Jiong and Chen Han were undergrad and master students working with me in this project. They did a lot of the work in building the Frogger, the modified Frogger. Super proud of them, and I really cannot thank all my lab mates for sticking out with all the pilot testing and all the nagging that I've done with you, and everyone else who pilot tested, because that really helped us iterate and get a good design. Going out for the funding, and finally, ready for questions, feedback, thoughts. Yes.
So if I understand properly, kind of the use case for this is that even though you're generating data from humans, the idea is to have NPCs explain their behavior, right? So have you thought about, like in current game architectures, NPCs are usually controlled either by a behavior tree system or a utility system. And so in both cases, the AI system already has an internal representation of the justifications for its actions, at least implicitly. And in fact, in the behavior tree systems, you'll even have operators in the behavior tree system to generate arcs, as they call them, to display that stuff. You could potentially build an interesting tool with this where designers could provide, candidate arcs, and the system would just learn off of the internal representation that's already there.
Absolutely, yeah.
The kind of workflow issue you have to deal with then is that probably the behavior tree is changing right up until ship date, and so thered be a question of the stability of the learning data. But that would be a potentially useful use case for this.
Thanks for the comment. I think that's a really good idea that we can look at the future where so the internal representation is already there. You don't have to make it up. So, okay, so that
Yeah, it's already a tree of I'm in combat mode, nice. I'm surrounded, and
So that's even to me that's a little bit of an advantage because you no longer have to make up the representation.
Exactly.
And at the heart of it, right, the rationale generation process, all it does is draws the association between the state and the rationale. I think you had your hand up, or did someone have their hand up?
I did, but
okay. Yeah, go ahead.
So, like you said, you wanted to like remove the black boxness of it, but it seems like you've just put another black box deeper in your black box.
Yes, I was hoping someone would bring this up. Yes, we are not necessarily opening up the black box because even if you opened up the black box, what you see in it is not interpretable.
Okay.
So,
I'll disagree to disagree.
Sure, and that's fine. But the reason why you put this rail of rationale in the same way, like if you showed me your fMRI scans right now, I wouldn't be able to interpret it because I don't know how to interpret them, right? Right now, you're communicating with me using a natural language system. That, to me, I would argue is as much of explaining a black box, which is your mind. But as long as context is fitting, and as long as our shared vocabulary is sort of situated, I feel like understanding and insights can happen. And I think that's what we were going for, which is why very carefully we did not use the word explainable, explanation generation. We used the word rationale. We were careful in not using the term rationalizing because that implies some agency. So it's just a rationale. You as the receiver of that rationale can judge whether that rationale was any useful or not. But I truly appreciate the comment. And that actually was something that we thought very deeply about and decided to take the steps as we
I was intrigued by the comment you made about the comparisons with human life. So I guess maybe a problem is that your users don't know which human you have to compare with.
No, so the Liebert scale, so the statement right before the weighted, it just is a simple statement. This rationale looks like it was made by a human.
By a human, yeah.
Yes.
What kind of human?
And that's the key part, right? I don't know if there is a better way of unpacking that to get at the question. And I think the tension here is the interesting part, right? Because we all have a theory of mind of what the relationship between machines and humans. The people who thought humans were error prone actually thought that machines were superior, and they actually rated more logical sounding, less structured, more structured responses as less human-like. Whereas when they saw that it's more wishy-washy and typos were involved. But what I think you're getting at, and help me understand this, I guess, how would you clarify that? Like, what human? So is it a designer, an end user, like?
You could rephrase it by something like, do you think this could be generated by or created by a human expert?
Okay, yeah, so we were not looking at that level of segmentation at this point. We looked at the higher human likeness, and obviously in the future work, we are planning to break it down to someone like you, the developer himself or herself, and someone who's an expert in creating the system. So you're absolutely right on that type. You can clarify who does what it does to get at that human likeness. Yes.
So, kind of getting back to what Adam brought up a moment ago. So you're not framing it as explainable AI, but you are presenting these rationales to users. Have you thought about what the consequences might be on the user side of giving them these rationales that potentially might be not representative of what the system is actually doing and how that might change their interactions with the system?
So the rationales are actually, we have grounded evidence in our own side that because this was why we did two configurations, right? We wanted to see, depending on how we vary the network structure, does what it looks at change? And we do have grounded evidence that, like, on the focus view, it rarely generates things. And like, if it's calling something a truck, we have the symbolic representation behind it to actually verify that it's actually talking to a truck. So there is some grounded evidence to the rationales that are getting provided.
Sure. No, I see that, and I agree that the rationales make sense at like a human level, but they're not necessarily reflective of what the reasoning of the agent, right? And so if the user is trying to influence how that agent is behaving, and they're getting these rationales that are reasonable but not representative, then that might make for potentially bad experiences.
Let Mark.
So I'm going to jump in here. Right?
Sure.
The true explanation for just about everything you saw here was I ran 10,000 simulations, and in states similar to this, when I performed certain actions, I got a higher reward over a certain amount of time with a higher probability based on some arbitrary reward function. Right? That is the correct explanation in all situations based on the way the agent is actually programmed, but is not actionable by humans unless you're a AI PhD who's interested in debugging reward functions or expectation maximization functions or something like that. So we explicitly steered away from truthfulness and focused on what would be useful for this particular audience, which would be in the game context, but also self-driving cars and other things, everyday people. What would they find valuable? We didn't know when we went in that we would get results that people would find actionable and useful. And one of the nice results by doing this qualitative study is to say, well, when we got explanations that said this, people said, oh yeah, I see exactly what you're talking about, even though it wasn't thinking about that. And I think that's kind of a nice, semi-unexpected, but nice result.
Okay. And to build on Mark's point, it is this notion of actionable insights, right? What are the insights that you can have? And that to us was more, I guess, operational than like this true notion of explanation. Sure. So yeah. Okay. One more? All right.
We can take it offline.
Okay, absolutely. All right. All right. No more questions? All right. Thank you.
Yep.
So the stream is back online. I believe we have a quick announcement before we get started with the next presentation.
Yep. So for those of you who were in before the coffee break, this will be redundant, but I just wanted to make everybody aware that there is now a Slack instance for the whole AIIDE conference. So everybody attending, even if you're attending remotely, if you're just viewing the stream, you can participate by joining that Slack. There's a channel for EXAG, it's just EXAG. And the link is written on the whiteboard behind me. So it's bit.ly/AIIDE-Slack. So you can join via that link. And maybe if you're viewing the stream and want to participate remotely, you can have some discussion and maybe add some questions through the Slack. Thanks.
Hi everybody, I'm Eve Gowell. I'm a fourth-year undergrad at Mills College, which is in Oakland, California. But I did this project as part of REU last summer at North Carolina State University. So I'd like to introduce my co-authors for this project, Marcus Ager and Chris Martin, who are both at NCSU. Well, Marcus isn't anymore, I guess. But yeah, so he's still hanging out with us. So this project takes an introductory look at how artificial intelligence agents can use nonverbal communication to better understand human intentions. Specifically, we used eye tracking to see how that can inform like the moves and choices made in a digital two-player version of the game Hanabi, which I'll explain the rules of in a second. So humans communicate in a lot of different ways. Obviously, one of the biggest ways that humans communicate that is not really translatable into AI yet is non-verbally. So we communicate through body language and facial expressions and eye movements and like tone of voice and just like a bunch of other like really subconscious things that we don't even realize that we're doing. So AI is being able to like see and interpret and eventually utilize these actions is kind of the next logical step towards improving, making like more natural human-computer interaction, in my opinion, I guess. So we're only testing eye tracking with this project to start, but kind of just because we had access to the technology. But yeah, so I'll go into that one more. These are Grice's maxims of communication, which you might have heard of before. But basically, he kind of says that people communicate based on a very like specific set of rules, and then assume that everyone else is kind of following these rules also. So we kind of use this as a basis of how our agent is like going to kind of communicate. We want our Hanabi AI to use these maxims. So. So to test out the like gaze pattern tracking, we decided to use a game. Games and like video games specifically are often used as test environments for certain research projects because they offer really like low impact, low risk environment, lots of test cases that are reflective of the real world, and they have like a very clear metric for performance. So like you know if you've won or lost, or if you're like succeeding or failing. Another example of this that I've found out about recently is how like Uber is testing self-driving cars using Grand Theft Auto because it has like a bunch, like you can simulate a ton of real-world scenarios like all at once, kind of without having to like drive 1,000 cars and possibly hit 1,000 people on the street or whatever. So that's just an example of like how games are being used to test certain things. But Hanabi is a very good game to test out eye tracking with because I will get into the rules in just a second, but it's a cooperative game. It's not competitive. It relies really heavily on inter-player communication, and players have very clear intentions, and there's like a very limited communication structure. Like you have a very clear set of rules of how you can communicate things, which kind of goes back to Grice's maxims. So you're probably wondering what Hanabi is at this point. This is just a picture of like the general pieces of the game, not really set up to be played. But so pretty much, I think the most complicated part of this week will actually be explaining the rules of Hanabi. But if you have more questions about that like later on, feel free to ask me. So you hold your cards facing away from you, so you can't see what you have in your hand, but you can see what everyone else has in their hand. And the goal is to build like fireworks. Hanabi means firework in Japanese. So you're building these fireworks or sets from 1 through 5. In each color, there's 5 colors, and then there's like, I think, 3 1s, 3 2s, 2 3s, 2 4s, and 1 1 of each color. I don't know if that makes sense, but yeah. So then there's 1 5 of each color, and then a couple of all the other numbers in each color. And so on each player's turn, you can either make a hint to another player. You can hint about the rank of some of their cards or about the color of some of their cards. So for example, I could be like, these 2 cards you have are 1s, or these 3 cards you have are red, and nothing else. Like that's my turn. Besides giving a hint, you could also choose to play a card. So if you think you know what you have in your hand, you can be like, okay, I think this is the next number in the set, and then you could play that one, or you could discard it if you think it's a multiple or something that's not useful. The game is played until all of the cards run out plus 1 bonus round, or once 3 mistakes are made. And the game is scored by how many correct cards are played. So if everything goes correctly and all 5 sets are completed, you have 25 cards on the board, which is 25 points, which is the maximum. But we're not just looking at score, we're also looking at how, like, we're not maximizing for score as a lot of other Hanabi AIs have done. We're trying to, like, see how human players and AIs give hints and how those hints are interpreted, both by the AI and by the human players. So this is our version of Hanabi that we made. I created this in Unity using C#. It's Unity 3D because we needed that to be able to integrate the eye tracking with it, but it's just like orthogonal view, I think, like from the top down with this. Yeah, and so here you can see like when you click on one of the computer's cards, which you can see the AI doesn't technically know, or the computer doesn't technically know what cards they are. You can hint rank or hint color, and then a little hint box pops up, either with the color or with the rank. So if it's grayed out, then you don't know the color of that card. And it's more helpful for your cards to see what they are. And then this is just the like play card or discard menu. So part of the trick to Hanabi is really like keeping track of everything you have in your hand, and you can do this like just like by remembering what hints people have given. I think it's typically discouraged that you write down all the information. That's like, but yeah. You can also do this by counting cards, kind of, since you know like how many of each card there are. You can count to find out like maybe if all of the other ones are played, then you know what color the one in your hand is going to be. So sometimes people also give preventative hints. If I drew a 5 really early on in the game and there's only 1 5 of each color, then maybe the other player, I don't want to say opponent because it's a cooperative game, but that's kind of what I think of every time. Whoever I'm playing with could be like, oh, you have a 5 right there, so I know not to discard it early on, and then could play it like later on in the game. So what do Hanabi agents actually look like? There are several different Hanabi playing agents that exist so far, and mostly these AIs perform by strictly either optimizing for score or by following a simple set of rules for interpreting humans' hints, but they don't do a good job of acting intentionally when giving a hint. So they don't, they're not like, okay, the person that I'm playing with is gonna think this when I give a hint. Because typically when you're playing the game, if you give a hint, you want the player to do something with that hint. If I'm like, you have a 1, then it's probably the one that hasn't been played yet. If I say like, you have a 5, or you have a red card, then it's probably the next red card in the sequence. Yeah, so Marcus made AI for Hanabi. If you have any questions about the AI, direct them to him. It's originally written in Python, and it's on like a web server. And it's like not integratable with eye tracking, so we made this version instead. But Marcus's AI is different in that it's intentional, which means that it uses players' intentions to interpret hints and rank possible moves. Kind of we want to know what each hint option is going to tell the human player about the game. So the AI is like, if I do this hint, what is the human player going to want to do based off of this hint? And so then based off that, it's able to like look a few moves ahead, rank possible options that could be taken, kind of decide what the human player is most likely to do, and see which which play option has the best chance of furthering the game and increasing the score in that moment. Which adds, okay, and then so eye tracking adds a whole another layer of intention recognition to the AI. Because as human players are playing together, they're not just going off of what's in their hand, what they know about the game, they're also like going off of people's facial expressions and body language, like this is, you're trying to like hint at the cards, but you're also trying to like hint at the cards, like kind of like get people to do what you want them to do with the cards, so which is something that the AI is not totally able to do yet. So we implemented the eye tracker, which could be super useful because our hypothesis is kind of that players communicate a lot of their intentions subconsciously through eye movements. We are in the preliminary stages of eye tracking. So basically we've hooked up the Toby eye tracker to our Unity game. Toby is really cool. I don't know if any of you guys have used an eye tracker, but it's like a Connect bar kind of. And it just like plugs into your laptop, and then you can kind of drag and drop all the functionality that you want and specify, like, if I'm looking at this thing, do this thing. But it does need like consistent recalibration, and it's not a perfect system. Like every time there's a new user, you need to recalibrate the eye tracker to that person. If the person has glasses, it doesn't work super well. So there's a couple nuances that we'd like to maybe mess around with. But besides the technology, we want to collect data to prove that the gaze patterns are actually reflective of player intentions. I'm pretty sure they are. No, for sure. So a few examples of like scenarios that we anticipate the eye tracker could be used. Like we think that players' gaze is going to be helpful, but there's a couple very specific scenarios that we want to look at. Also, every time I say look or see, I am making fun of eye tracking. So yeah, a couple different scenarios in which the eye tracker could be useful. If a player is trying to decide between two cards, like maybe they want to give a hint about one of the cards and they're not sure which one, they would be looking between those two cards, and maybe they give a hint about one, the AI could be like, okay, but it was looking at this other card, so we're gonna like flag that one or add like a +1 to the rank of what I should do with this card or whatever. I'll keep that in mind. And then another scenario is if a player is maybe trying to figure out the color of the card in their hand. They know maybe they have a 1 and they're trying to figure out which color it is. They could be looking at the cards on the board in the discard pile in the AI's hand, trying to count the cards and figure out which color it could be. The AI could then be like, oh, maybe I should give a hint about that so that the player is able to do something like further the game. Also, another scenario that we think will be helpful or further with the eye tracking is gaze duration. If somebody draws a card and the player is like looking at that card like for a significant amount of time, whatever significant scenario, then the AI could be like, okay, that card probably has some significance to the game. Maybe it's a 5, maybe it's the next in sequence. Even if the player chooses to play a card or discard or not give a hint about it, or give a hint about a different card on their next turn. So these are just some examples of possible significance that eye tracking data could provide. There's probably more things, and also these might end up not being true once we gather a bunch of data. But our implementation of the eye tracking also, I'll explain what this picture is showing in just a second. But our implementation of the eye tracking currently has like a little dot, like a little X that moves around wherever the player is looking, which is really cool for debugging, but not super helpful if you're trying to play the game. It's kind of distracting. So besides that, we also have a script that generates a heat map, which is kind of seen here. The heat map that gets saved is actually just like a blue screen with all these heat points, like colors, like splashes on it. But this is the kind of like overlay of what the heat map corresponds to in the actual implementation of Unity. So basically what we found out from doing a few trial runs of the eye tracking is that players do actually look at the cards while they're playing, which is awesome. Like, that was like if they didn't, I don't know. And another thing that we've kind of realized, which is not surprising at all, but players look at UI elements a lot more than we kind of anticipated. especially the especially like the UI elements that pop up during the game. So the like player menu and the like play options menu and the like hint tokens and mistake tokens as they like appear and disappear. Players are like drawn to those items. This like we didn't really anticipate this, but it makes a lot of sense. So currently the full heat map, just the like blue screen with the flash, is saved at the end of the game without any like data about what was going on during the game. So the next step in future work that we want to do is to be able to better correlate the gaze patterns and player decisions. So I think one way we are thinking about going about this is by maybe saving a screen recording of the game as it's being played, with either the heat map being like generated overlaid onto the thing or like next to it, so that we can kind of compare what a player is looking at throughout the game, not just like what they looked at after the fact, which will help us correlate like their intentions to what they're actually looking at. We do have a lot of other future work. The first step, obviously, is going to be implementing Marcus's AI into this Hanabi Unity version, because it's not currently right now. The computer just makes like a random decision and plays a random card. And then our next step is to figure out, is our hypothesis correct? Are players' gaze movements directly correlated to their intentions within the game? If so, how are they related, and how can the AI interpret that? We want to do that through doing a bunch of user studies, having people do playthroughs of the game with the AI. During the user studies, the players will be aware of gaze tracking, which we expect to have an impact on like how they're interacting with the game, maybe what they're looking at throughout the game. So to work with that, we want to have multiple test playthroughs with each person. Randomly, some will have eye tracking, but the AI won't use that to make any decisions. And then other times, the eye tracking will be integrated with the AI. And then we want players to answer a survey. For example, some questions could be, do you feel like the AI understood the hints that you gave? Did it do what you wanted when you gave a specific hint? And did the AI hints make sense to you? Did the hints that it gave like further the game, if it was like, you have a 1 there, and then you tried to play it, and it wasn't like the next one in the set, then why would it have given you that hint, right? Other like less significant work that we want to do on this game is to clean up the UI, add multiple player options, which could be multiple human players or having multiple AI players. Hanabi is typically a 2 to 5 player game, and it's a lot more interesting with I think 3 or more players, because if there's just 2 players, sometimes it gets stuck in like a loop of just hints and hints and hints, and then the game kind of doesn't go anywhere. So in conclusion, we believe that eye tracking will have a huge impact on intention recognition in artificial intelligence, specifically in Hanabi. Hopefully in other fields besides gaming can benefit from eye tracking. For example, it's already being used as like an accessibility feature in a lot of cases, and in networks or cybersecurity, I guess. There's some projects going on about like eye movements as a, I forget what it's called, but like as a passcode kind of barrier. But it definitely will improve and make a lot more natural human-computer interactions. If the AI can like not only go off of just the movements that are being made, but really interpret those movements and really interpret those actions, and like, I don't know, being able to anticipate human needs based on eye movement, being able to just act on it. So if you'd like to play the rough version of our Hanabi Unity version, I have it on my laptop, so hit me up if you want to play it. You should all get Hanabi, it's really fun in general.
That's not my email, don't email me there.
Oh, sorry. What is it? I'll send it later, sorry. Yeah. So if you have any questions about the AI itself, definitely talk to Marcus. Yeah.
So thanks for the talk. It's interesting work. Have you noticed in your experience playing Hanabi with other human players, if other human players use like where their counterparts are looking as additional hints?
Yeah, so as I played Hanabi, I think I'm not like, ooh, this person's looking at that card, but I'm kind of like recognizing what people are looking at, what people are doing during the game. So if I'm playing the game, I'm like, of Hanabi, I'm seeing the other person and they're like maybe looking around at the board. And so I can like see based on body language. So I think this is kind of the first step towards that sort of intention recognition. I don't know if we're kind of trying to figure out if eye tracking is actually the best way to do this, or if maybe other body language is going to be more useful. Yeah.
Is it me? Yeah, great. Yeah, it's a pretty interesting talk. This actually relates me to some competitive scenario. I know that, I mean, this game is, cooperative.
Yeah.
But if this is used in a competitive environment, let's say, obfuscation becomes a problem. Let's say if I'm a player, I circle my eyes 3 times clockwise, 3 times backwards, then do any actions. Do you feel that the system will be just played around?
Yeah, like, are you asking if it, how this could be used in a competitive game? Yeah, so I've thought a lot about like how this could be used in other games like poker, or something like that, where body language is also a really like integral part of the game. Or bridge. Or yeah.
I think in bridge competitions, I mean, just simply people are not allowed to see each other, and you prevent people from looking at their eyes.
Yeah, so I've thought about it a lot, but I don't really know like what would happen. I'm sure there's a lot of ways that you could like cheat the system. But we kind of chose Hanabi specifically because it's a cooperative game and it makes it, this is like a good environment to test out that like nonverbal communication. Like, if you did it in a competitive game, it would be, people would be more inclined to try and cheat the system instead of trying to get it to work.
So I'm curious about going forward, how you're planning to integrate this with the AI, whether it's going to be more like handmade rules, like the user is looking at this card, so increase its importance, or if you're going to go for a more like learning approach that the user is looking at this card, let the algorithm figure out what that means.
I would see what Marcus has to say about that.
I can answer this. Basically, the way I intend this to be is you already have established AIs, and they make decisions based on either learned rules or hand-coded rules or something. And basically, the eye tracking just provides like some additional nudge in one direction, but I wouldn't rely too much on it either. So I think it's basically just a tiebreaker if the existing system has a situation where it has 2 actions that are equally likely. And then it depends on if it's a learned algorithm that you incorporate it in your learning data, or if it's a hand-coded rule system, then you make the call of how do you incorporate that. But I feel like this is kind of orthogonal to developing actual Hanabi AIs. Like the idea is you can add this to whatever to resolve some ambiguities. That makes sense.
Fascinating talk. I really like the focus on the nonverbal side of communication, often gets overlooked. I'm curious if it may be feasible to look at integration of modalities at the sensor level. So you're looking eye tracking as one modality.
Yeah.
So Affectiva has this notion, an SDK, an open source SDK that can be used to look at gestures as well. If it's an embodied communication, if it's not just happening over distance with the screen, that may be one notion of investigation as well, to actually highlight what is eye tracking actually giving us.
Yeah.
Right? Because one of the harder pieces of eye tracking studies is to get to that association, like I'm looking here because of whatever.
Yeah, we're really trying to like figure out.
That's the harder piece.
Yeah.
One piece that I found helpful is you can make users, when you're doing the initial testing, to go through a replay of their own gameplay.
Yeah.
And sort of like look if what we thought they were thinking is aligned with what they say.
Yeah. We've been thinking like the Toby eye tracker isn't the best.
Oh.
I don't think it's the best. I don't like we haven't really used any other like systems, but I think using other technologies and other like not just eye tracking, like other body movement, body language kind of tracking would be really interesting. This was like kind of a short project that I did last summer, so I don't know how much further work is going to be done. Marcus says no.
During the presentation. Can you send me your paper, or no, just so you know, this paper is broken on the side.
No, it's fixed.
Oh, it's been fixed? Oh, okay. Never mind.
Yeah, you might need to refresh the page a bit to get it out of cache.
Okay.
I was gonna do it last night, I forgot, and then I got reminded this morning.
Okay. I got it.
Okay. Hi, everybody. Welcome. So my name is Nadim Barika, and I'll be presenting this short paper we had in the proceedings of the workshop on evolving non-playable character PC behaviors and AIIDE proxies. The joint work with myself and my colleagues, some of which are here. So Mark is in front here, Morgan is sitting down there, and Matt Brown is out of town. Okay, so let me start from the end of the talk. We have no results yet, so there's nothing to present, but fear not. I have a few exciting questions, and I would like to get some feedback, in particular if we're missing some important piece of work that you guys know of and we don't think you guys know. And we also, since it's early in the project, we are interested in collaborators. So if you yourself or somebody you know is interested in collaborating, definitely pass it on to them. The paper itself, of course, is all the papers in the workshop. It's free available on EXAG.org, so you can see it there. So let me start quite far out. Is what artificial intelligence? And I think there are two primary answers to that question that I hear people give. One is more practical, perhaps, is to have AI assistants. So here the diagram from Google. This is Google Duplex, which presumably calls merchants and restaurants and so on on your behalf and talks to them and so on. And of course, we have self-driving cars, Siri, and so on. However, there is a second reason to do AI, and arguably the initial dream of AI was to use AI as a sort of petri dish or a test bed or sandbox of cognition. So to understand better what intelligence and what cognition is. In my talk, I'm going to talk about both, and I think what we are proposing, what we're doing, actually addresses both parts to some extent. Okay, so we all, of course, know the rapid advances in AI. So this is a quote from DeepMind. When they were talking about AlphaGo Zero and promoting it, they said that AlphaGo Zero, the technique, is more powerful than the previous version of AlphaGo because it's no longer constrained by the limits of human knowledge. It sounds, of course, great from a marketing perspective. Of course, AlphaGo Zero does have human knowledge, the topology of network, for instance, and the rules and so on. But we've all seen, in particular in games, there's been a lot of work in Atari, both from a reinforcement learning perspective, things like DQN, as well as Neural Evolution. There has been some recent work which shows some great performance. We have personal visual assistants, autonomous cars. So AI is here to some extent, and it's probably more and more of it is going to come. And of course, when a big change like that happens in a society, people feel uneasy in many ways. So we actually had here in Alberta, we had a meeting about half a year ago where the government asked the university to provide some questions to provide answers to the questions that the general public were asking. And a lot of them were focused around, am I going to lose my job, right? What's going to happen to me? How are things going to change? And they're fair questions. I think if they're good questions, I don't have answers to them. But I'm going to suggest a way to look at some of them. Okay. What's also interesting about this picture is, of course, from Terminator 1, but it's been processed by a deep neural network, which basically transfers style from a certain painting style onto this photograph of Schwarzenegger. And so it's not just anymore human creation,
is now partly processed by machine learning. Okay, so personally, I would like to study emergent AI, and let me explain what I mean by that term. So, in terms of the physical reality, we could study AI in terms of physical agents, such as self-driving cars. This is an article from earlier this year on Ars Technica about California now allows driverless cars without a human behind the wheel. They may have changed that later, but I think this is an Uber car pictured here in a particular photograph. So we could do that, but of course there are risks attached to it, and many people are trying, right? In particular, Google included with one of their branches. I'm proposing, as has been proposed many times before, is to use video games as a sandbox to study some of those issues, but not just because they're available, but because it's also fun. So the screenshot on the right is, of course, from Fallout 4, and the whole plot of the game is about AI and their acceptance in society. They're called things in the game, and there's, in this particular moment here, this is a deciding moment that you play the game. Depending on how you treat those 4 things, the rest of the game will be somewhat different. Okay, so I'm proposing to hit both applications. One is this petri dish of cognition, and the other one is something more practical or short term. So on the right is the more practical in the short term, right? So what I would like to do is to procedurally generate NPC, non-playable character AI that is light, which helps game developers with their expense, labor expense, which is reliable and is acceptable to quality assurance of some sort, which is player adaptive and it's persistent. So what I mean by persistent, it's not just adaptive from the short term, and the effects not only last in short term, but long term. So to come back to Fallout 4, if you were to take out all the ghouls in the game, the ecosystem would change tremendously, not just some other character will make it different quickly. Okay? So we would like that to play towards increasing player engagement, which could be measured in different ways. Probably the simplest way to measure it would be to see how long people stay and play the game voluntarily. That's probably not ideal. There are better ways, but that would be a cheap proxy to measure. And ideally, we would also like this to be compatible with existing NPC frameworks. A lot of companies use behavior trees. Some of that comes within the game engine. So if we can somehow add that insert, that would be great. On the left column, this is a more petri dish of cognition angle. So I would like to study AI agents with behavior which is emergent, non-scripted, perhaps even self-directed. So instead of creating intellectual slaves, is there any way to see, left to its own devices, where would those agents go? Right now, it's perhaps not very interesting, right? But I think this is something we have to think about given the rapid advances in AI. Right? So when Siri talks to you, what prevents Siri from sometimes lying to you? Right? So right now, it doesn't have it, right? But could it intentionally lie to just so you would stop bugging it? Right? So right now, it's still domains of science fiction. So for instance, the movie Her has very advanced version of Siri, motion advanced version, and there's interesting developments because of that. I also want the behavior to be novel and surprising in some way. I will talk a little bit about that later. And then as the color drains, or the brightness drains, this is more and more longer term objectives. I would like them to have their own motivations, or at least to study what they would be, those motivations. And not because I just want to spend a lot of time in creating self-directed robots necessarily, but I think it's critical that we study that, because in my opinion, it's going to happen one way or the other. And if we are unprepared, it will be worse. Agents that could be introspect and explain themselves, that's perhaps even shorter term. One of the criticisms of deep networks that is currently leveraged against them is that explaining them is difficult, and there has been some progress on that, and perhaps we can get some of that here as well. Okay, so for related works, there's been quite a bit. I'm going to mention one example, because it was presented at EXAG last year in Snowbird, Utah. So there's a game by Polymorph Games. It's a commercial game. You can buy it on Steam. There's a new one coming out, Project Pasteur. So this game, it's basically a version of Space Invaders, where the creatures, the enemies evolve as you play based on your lifestyle. So they are actually running Darwinian evolution, very accelerated on the back end as you play the game. That's why it's called Darwin's Demons. And it's good, but the game is quite limited, right? So you're basically shooting, and what they gain is different techniques to avoid your projectiles and get to do better. Okay. So I want to do something similar, but much more open-ended, not just for shooting up in a 2D game. Okay, so the approach we've been investigating in my research group for a while is multi-scale machine learning. What it means is that the agents learn within a lifetime, or they can, maybe using some form of reinforcement learning or anything else. Even though the agents themselves may be simple, because they exist in a colony, you can have difficult or complex behaviors emerging. This is a well-known phenomenon that complexity often arises from interaction between agents, and perhaps one of the reasons why games are fun, especially if people are playing there. We would like to be able to detect behavior automatically, interesting behavior. Of course, the word interesting is very fuzzy here. And so right now we're approximating this functionally as anomaly detection. So we have automated methods for anomaly detection. So as these agents progress over time, can we detect something anomalous? And it could be a bug, which is actually useful for game companies since they can automatically detect bugs. Or it could be not a bug, and I'm going to show an example in a second. And I'm going to skip this part. So what we've built so far is an environment where there are small agents running around. They have deep neural networks for each of their brains. Each brain is unique. It's encoded in their genes. So we're basically running neural evolution. Here, we start with smaller brains. Bigger brains can evolve over time. Of course, bigger brains, just like in biological brains, consume more energy. So if you have a bigger brain, you better use it for survival, otherwise it's survivability. There is no discrete generations, no predefined fitness function. This is much more A-life-ish. So if you're familiar with early work by Michael Littman and David Ackley in evolutionary reinforcement learning, it's similar to that. You can have grandparents living together. There's no any particular moment when we compute a fitness function. So the fitness function is, of course, there, but it's implicitly encoded within the survival task, within the physics of the environment. Now, what's also interesting, we're currently not doing any semantic parsing of the environment. So the agents basically have a retina, and they see RGB values for the pixels. And of course, they have to interpret what the sources are, what is friend, what is a foe, what to avoid, what to eat, and so on. And also I should mention that they do have some abilities to communicate. This is still very early on, and we've been looking, one of my students have been looking at things like altruism and a sense of selfish gene by donkeys. Okay, so let me give you one example. Even though the environment may appear trivial to you, it immediately leads to some interesting phenomena. So a year ago, we discovered that there were, let's call them rabbits. These are the agents which don't eat any other agent. They eat resource. Let's call it grass, the green stuff here. We discovered that there were rabbits which disliked that resource and yet lived for a long time. So we spent about a week debugging it, trying to find how is it even possible. It turned out that there is no bug. So what was happening, if you would actually place those agents in the environment by themselves, they would certainly die because they're terrified of the only food source they have. Okay? However, they also happen to like or to evolve to follow other agents which also eat the same resource. Okay? And so you would have two types of rabbits, the ones which eat grass and the ones which follow the ones which eat grass. Because eating was automatic, as soon as you're on top of grass, you consume some, you just have to be in the right place. And so you get this groupie rabbits following the guru rabbits. Now, there's a benefit to guru rabbits as well. If a wolf shows up and I'm surrounded by a whole bunch of other agents, the wolf is likely to get one of them. Right? It's called dilution effect, and it's known in biology. Okay. I want to mention one more phenomenon which we didn't expect. we allow the color of the rabbits to be genetic. So you can be any color you want if it's in your genes. And so what's interesting is that early on, the rabbits learn that the grass, which is green, is good. And then, if you unlock the color themselves, they become all sorts of colors except green. And the reason they cannot be green is because if they are green, they treat themselves as grass. So they're very narcissistic. They sit there and they don't want to go anywhere because they already have a lot of grass right here themselves. Except they can't eat themselves, so of course they starve to death. So green rabbits don't survive. So this little phenomena, they sort of anecdotal, but they emerge almost on a weekly basis, right? And we probably missed a whole bunch because we don't stare at the screen all day long, right? Okay, so what's interesting about this is that so far we can run everything without humans involved. But that's perhaps not interesting in a video game, right? In a video game, you want the characters to be somehow informed by players, right? So Fallout 76 is out today, and it has lots of AI-controlled creatures, even though they say no NPCs, but there are monsters, for instance, in the game which are AI-controlled. So now the internet is collectively, or the players are collectively playing Fallout 76 is always online. What would be interesting is those creatures somehow evolve. Right now they can't, right? They're just finite state machines effectively in the game. So what we want is to evolve those rabbits and wolves in response to people in a game-like environment. The issue is, okay, so at first hand, at first blush, it's easy. You just plug people in as avatars, which video games do all the time. That's how we play the game, right? And of course, in real life, you're searing your cell phone, so to speak. The problem is that evolution takes a while. And so games like Darwin Demon, shown up on the right there, actually did a lot of tricks to make evolution manifest itself in a short amount of time, because otherwise you're going to give up on playing the Space Invaders. Nothing is changing. Or maybe you're just going to play it even nothing is changing. So humans are slower, right? So you don't have as much time if you're running with a human as opposed to if you're running headless, so to speak. Okay. So the idea is to have a tractable human-informed evolution is by creating AI proxies of humans. So you have real humans playing the game, you observe their behavior, and you create a proxy. So literature has also been known as clones. Right? So there's a paper in 2016 which actually does some study on that. Of course, we all know Forza Motorsports, which did that with clones of driving, or abstraction of driving, or drivatars. And my student David Tu and I worked on this for a while in terms of role-playing games. So you use the human play data to create the proxies. And now that you have those proxies, you don't need humans, for a while at least. You can run a few additional rounds of neuroevolution with the proxies, and then release the new agents, download them to people's console. They play again, you collect data, beam it back, and basically continue the cycle. So this is a figure from a paper that Morgan prepared on that. And we are actually implementing this for not a video game yet, but for interactive art installation. And just because we thought, well, what's the worst that can happen? So what's going to happen in next April in 2019 here in Edmonton is we're going to have a large room. The agents are projected onto the floor because there's a projector facing down, or maybe multiple projectors doing that. A general public off the street wanders in, probably has to sign something, right? And there's also an overhead camera which tracks them. So it immediately creates an avatar, kind of like Microsoft Kinect, except we're not projecting infrared dots. And so you instantly have an avatar. So you just walk around the room, and you're present in that two-dimensional flatland of those creatures. Now you can interact with them, maybe by using gestures, or maybe because you just sprinkle this grass as in your wake as you go. We haven't quite decided that yet. Okay. So, however, because we're tracking you as a player, and there could be multiple people in the room, we have all this data of your movement patterns. So the idea is in the daytime, real humans are at the installation. In the evening, the installation shuts down, no access. So those traces are clustered, and these clones or proxies are created. And at nighttime, we turn off visualization, and we run as many generations of this. Generation is probably not the right word because it's good duration, but as long as we can, this A-like evolution, neuroevolution, without the actual visualization, so headless. We release the evolved creatures next morning, and the cycle repeats. So this is going to run for 1 month. So the interesting question is, what happens at the end of the month? How are the creatures at the end going to be different? And we can run a parallel evolution. We can start with the same population and run a parallel one where no humans are evolved at all, right? So, or no proxies. So you can have all the baselines and competing models there. And then the months you can compare the behaviors of creatures. This is not, we don't have this yet. This is from a team called Team Lab. And they have some similarities with the person walking here and the projections on the floor, but very different purpose, very different identity. Okay, so to wrap up, I'm arguing that machine learning for AI necessarily causes us less direct control as opposed to creating finite state machines by hand or behavior trees or whatnot. And therefore, we need to study emergent AI. Maybe the G here is a general, maybe emergent artificial general intelligence. So I'm proposing to address with this project 2 goals. One is the plan-informed procedural comment generation for non-playable character AI, NPC-AI. And the other one is just all these musings about artificial general intelligence, what it means to be self-directed, what it means to have core communication between the agents, right? Would they learn to lie themselves? So if you think about work of Michael Matthias' group on where the agents can lie to themselves, to each other, deceive each other, a lot of that was programmed. Can this emerge from scratch? Can a language emerge from scratch? So the work of Angeliki at DeepMind currently relates to that. So I am looking for people to talk to me either now or in the break. This is a lab website, agi-lab.net. Thank you very much. Questions? Comments? It's crazy. Yes.
Do you feel that, the talk is good? Probably it's just my misunderstanding, but if someone, being is adversarial, he or she decided to come into the system and do something bad, do you feel that the system itself can recover from it?
Yeah, that's an excellent question. So I think well, I don't have an answer because we don't have the system yet, but my speculation would be that the amount of damage one person can do would be limited in so much as there are quite a few people involved, right? So if it's only one person, then you can steer the whole evolution further. But if it's 10 of us playing this game, then your actions, unless we all agree on being, playing a single way, perhaps your input will be diluted by actions of other people somewhere.
I see. So it's more like the mode of the actions will be learned. Either it's adversarial or not.
That's right. It's not even clear what adversarial really means here because in this pseudo game, there is no real score, there is no point. It's not even clear what the objective is. Right? That's why I'm hesitant to call it a game yet at this point, but more an art installation. Right? Because our installation is fuzzy term. Yeah, good question. Yes?
Do you have any structured way of studying emergence, just say?
Yes. So the only formal way I currently have, okay, so let me give you two parts, answering 2 parts. So in terms of mathematically, the way that we are planning to detect any emergent behavior is treating it as an anomaly, right? So for instance, you can use deep-out encoders, temporally extended deep-out encoders. These are the things that people use for fraud detection, for detection of events in a video stream. So if filming something, pedestrians walking the street, suddenly a guy on a bike comes. That's an anomaly if the system is trained for pedestrians only. Right? So things like that, we have experimented with them, and we're making progress on that. The other part is a little bit fuzzier, is to run some user study at the end. So for instance, at the end of this month, when we have 2 versions of agents, the agents which evolved in evolution formed by humans and agents which never saw humans, could then an observer, a human observer, tell the difference by looking at their behavior? I don't know if that gets to the question that you asked.
That was an open question.
Okay.
Yeah, absolutely.
Yeah, great. Any other questions, open or closed for any time? Okay, well, thank you.